for giving us this talk. And the floor is yours.
Thank you, Daniel. Thank you, everybody, for attending today. I will share my screen so we can go directly to the short presentation that I have. The idea today is to have a conversation about the high performance computing in the quantum era. So I have a small presentation that will take me about maybe 20 minutes. And after that, I will be glad to answer any questions that you have, if I can, and to have a discussion about the implications of having this integration between quantum computing and HPC and the current trends and all those things. So just give me a second. I will share my screen. Okay. So the issue is known as quantum-centric supercomputing, and it's mainly the trend of having high-performance computing physically close to HPC centers in order to improve the full performance of the calculations and the simulation that we are going to run. So just give me a second. I will start with this. This is just, I would like to thank Daniel and the Qiskit Fall Fest for this invitation to share my thoughts with you. And what you see in the right part of the screen, it's two news. One was from September 5, 2024, and the other one was from May 2, 2024, about NVIDIA joining quantum computing systems, start exploring on that issue. And the other one is related to Oak Ridge National Labs that is getting a quantum computer. For example, the Barcelona Supercomputing Center is also getting a quantum computer. And the question is how this will be related to high-performance computing, what kind of impact it will have, if it will allow us to move to improve the efficiency of the systems that we currently have, and to be able to use quantum computer in real applications. And by real, I mean not only in real problems, but sometimes in real-time problems. Okay, so the agenda, it's only 4 points. We'll talk about quantum-centric supercomputing. But we will talk about also the core components of this architecture. The latest things that Qiskit has done in using or in adding to the APIs and all the things, the functionality that is needed to have a good coordination between the cluster and the quantum computing, and what is the road ahead in this case. So let's start directly with what is with high performance computing. As you know, just give me a second. In classical supercomputing, what we have is that we use parallelism. Originally it was via CPUs, and later we talk about GPUs, TPUs, and all those accelerators that are specifically designed to accelerate the calculation that we need. And it's to perform complex calculation. By complex, I want to make clear what it means. High performance computing is useful when you have a task that can be parallelized. If the task cannot be parallelized, it's useless. So the idea of having these big clusters is to have a way of sharing the resources. So when a researcher or when an engineering group or anybody needs to run a massive parallel application, can run it in short time, and in that way that resource is shared by everybody. We started with CPUs late in the 80s. Then the GPUs were useful because they were initially designed for games, and in games they use a lot of matrix operations, and matrix operations can be done in parallel. So and in solving linear problems, solving differential equations, and all the things, those matrix appears a lot, so it was helpful for that. What is the idea? Is the idea that we need speed and a good scale. The velocity or the speed is measured in flops, number of of floating operation points that are performed per second, and the fastest machine in this moment are in the exaflop scale. That exaflop scale means that we are in about 10 to the 24 scale, 10 to the 24 flops, floating point operations per second. And what is the role that high performance computing can play in a quantum center supercomputing? Is basically devoted to two tasks. The first one is to manage the quantum execution loop. That means prepare everything to be sent to the quantum computer, send all the information, and manage that execution loop. With an interesting point is that we can have, or the idea is that in some cases, in some algorithms, we need intermediate measurements. Why? Because it's a quantum algorithm that is iterative. We have to repeat, or we have to use a quantum circuit many times, and sometimes the kind of circuit that we use or the parameters that it has depends on values that are measured in the middle of the algorithm. So the cluster, the HPC cluster, will have a role in analyzing that information. Usually it's very fast because mainly it's just a decision. It's according to this value, do this or do that, but it's important that it has that role. And also we have error correction and mitigation routines in real time, which means that we have to, in many cases, we can use error correction and mitigation routines, which means that we can have to post-process the results in order to mitigate the error that we have in real time. When we talk about quantum computing, and I will be very, very fast in this because you already have some background on this. Basically, we have what we are using quantum mechanical effects in order to process information. Okay, and the key principles that we use are superposition. It means that qubits can exist in a superposition of classical states. It means that it can be simultaneously in many states, and that's one of the big powers that we have in quantum computing. Entanglement, that's that we can establish a strong correlation between two qubits, in the sense that when you measure one, the change of the other one will, the state of the other one will change accordingly to the result that you have in the measurement. I just want to say here that entanglement, when we talk about entanglement, is the maximum correlation that we can have, but in a quantum system, everything is correlated with everything. So it's just that we have that entanglement when it's the maximum correlation that we have. And then interference. Interference basically is that we have a quantum states. We have, for a quantum state, we have the states, the different states or the basis vectors for that space, and each one has an amplitude associated. That's what I mean is that the state of a quantum system is always a unitary vector, a normal vector in a Hilbert space that has two the spaces over the complex, and it has two 2D dimensions. So it's being on the complex, we can use that the amplitudes for representing the vector as a linear combination of the bases. Each base is multiplied by a complex amplitude, and that amplitude they can reinforce. When you combine them, they can reinforce each other or they can cancel. That is what we call constructive interference and destructive interference, and it's really important in many algorithms for using those properties. The goal that we have is solve specific classes of problems, mainly simulation, optimization, factoring, and we're trying to solve processes that are, problems that are intractable for most powerful classical HPC systems. And there is something that is very interesting. It's that since Deutsch proved the equivalence between the quantum Turing machine and the Turing machines, quantum computing is not breaking the computability limit, but is breaking the tractability limit. That means that allows us to solve problems very, very fast. Okay, and one thing that is natural and it's important is that the idea is that we use quantum computing when it's more cost effective than classical computing. And by cost effective, I mean not only that it costs less, that it's not really the case in this moment, because you know how expensive it is to use a quantum computer, but I also mean by that cost in time or in precision, that by using a quantum computer you can get answers that in a classical computer will take a very long time or will be not as precise as the answers that you can get with the quantum computer. So the programming model, and there are two different main models. The one that is with quantum gates and circuits, the Qiskit is based on that, and that provides universal quantum computing. And we also have some manufacturers who build machines that are devoted only for solving quantum annealing process. When we are talking about this integration, mainly you will see it's not exactly independent of the model that you use, but in principle you can use both models without any problem. We'll talk about Qiskit proposals and how it's the roadmap that in Qiskit IBM is proposing for the future. But I think, and it's one of the things that I really like about this, that is more a general overview of the things that we can do for integrated quantum computing and supercomputing in order to get the best from both worlds. So what is the idea of that quantum classical integration? Is to have a single unified system that integrates quantum and classical hardware. It's kind of a generation of what we have currently in our data centers, when we have integrated CPUs, classical CPUs with many cores. We have GPUs, we have TPUs, and we have also some ASIC circuits that are integrated. So when you submit a simulation or you need to run a model, you have to specify which resources do you need. In this case, we can see this quantum computing as another resource that must be available, and that's a very important thing in order to achieve the answer, the wall times that we need for our execution. So and that is a classical problem that also appears in HPC. And why? Because if you say I have a model that I can run in my resources and it will take, I don't know, 3 weeks, and if you run it in the cluster, it will take 10 seconds. But you try to run it in the cluster and I will have to wait in a queue for 1 month, then it's more effective for you to run it in your machine or in your resources where it takes more time, but you have, at the end, what is important is when you have the results. So one of the challenges that are here is that we have to integrate that quantum computing with the data center in a way that it's a resource that the programs can reserve and can use it in a very efficient way. The original way of work has been to use to have access to these machines using cloud technology, but now the idea, what people are doing is that trying to buy a quantum machine and have it physically close, physically located in the same data center with high performance computing. So the communication between those resources is very effective. Okay, so I will talk a little bit about this later, just give me a second. So now let's move to the next point, is core architecture components. In this case, I just wanna specify quickly that Qiskit is making a change in its architecture, in the way of working. For example, one of them was the pulse package was deprecated. That means that you cannot use it anymore. And the idea is that the role that you have with the pulse packet, where you have control over the analog, the pulses, everything that is going on physical level, will be done automatically by the quantum center supercomputing. It means that it will have another case, another layer that I will go on that a little bit later, that will be responsible for doing that. The other thing is the users must work in the level of quantum gates and circuits. What I mean, and it's clear that you understand here that digital does not mean that we will use the quantum computers like we use a classical computer, because in that case we will lose all the power. What I mean, this at the digital level is digital means not binary 0 or 1. The digital here means an interesting thing is that even when we're talking with quantum computers, we have a discrete set of possible states. So that's digital in that sense. So I mean it's digital as opposed to analog. It means that it's discrete as opposed to continuum, but not meaning that is 0 or 1. The responsibility of that center that will integrate those is to manage it will have to handle the complex analog pulses control, hiding that complexity from the user. You know that one of the problems that we have now is that the level of noise that we have, and we have to correct that. We have systematic noise, we have random noise, and how to try to avoid that, to eliminate that uncertainty that is introduced by noise. And that's why we're starting to talk about digital qubits and physical qubits, where a digital qubit can be represented by a group of physical qubits that are working in a configuration that allows noise reduction. Okay, and this is the foundation of that new architecture. So in the architecture, we have three basic things. One is the math compiler that will transform high-level user code into optimized low-level instructions. And what I mean by optimize is that it has to replace the things that we did with Pulse. It has to automate that. It's mainly the same thing that has happened for example, in software development for HPC, where every day we have new tools in order to handle parallelism more automatically. But it's just something that is starting, and we have to find a way for doing that, so that the experience that we have, the things that we have learned, can be automatically added, and how to handle the things that we are just discovering about that. The next thing is the HPC bridge. That is the one that is responsible for the high-speed transfer of data between the cluster and the quantum computing. is the same that has been done with, for example, with GPU cards or with TPU cards from NVIDIA, for example, where they have a special switch that works on the on speeds of the order of terabits, something like that, in order to move the data very fast. So the HPC bridge is the one responsible for minimizing the amount of time that is spent sending information from the cluster to the quantum computing and from the quantum computer to the cluster. Finally, is the runtime engine, which is responsible for executing the quantum program, or like physicists said, executing the algorithms, running the algorithms. It handles the state management of the infrastructure and all those things. Okay, so let's talk a little bit about each one of them. The smart compiler will receive a circuit defined by the user. You know that currently the way that we develop quantum algorithms is just a circuit design. So it will receive that circuit design. We mentioned there application of that problems because when we have layers of software that can solve or that can automate some things, for example, how to represent a CUA problem, quantum unrestricted binary optimization problem, to solve it with QA. So it's something that is well known, and so you can find tools for doing that. And the key functions will be optimization, which includes basic gate mapping, resource scheduling, circuit simplification, all the process of transpilation, all those things. Error suppression, it has to apply techniques like dynamic decoupling or mitigation in the of the errors in the measurement process, and also provide the abstraction management. So in that way, the programmer or the developer can think about logical qubits instead of physical qubits. It will be responsible for doing that translation. The runtime engine connects connects the quantum hardware to those classical HPC resources. The goal is to ensure fast and low latency data communication and the execution of the problem. Okay, so that's what happens during the execution. Enables real-time feedback for error correction and in-circuit measurements. The purpose is to execute the execution environment for the quantum program, and it orchestrates the smart compiler with the HPC bridge output in order to share that information as fast as possible. And is responsible for handling the program state, the result collection that we have, and the resource allocation, so it can be used and is available on time. The Qiskit program model has made some changes. The idea is to have a unified system image where the user can think about a hybrid system, quantum computing with HPC as a one resource, and it can be scheduled in the same way that we scale with traditional resources in this moment. The idea, and it's something that has been done in computer science for many years, is to focus on the intents of the algorithm rather than in the hardware. If you remember, back in the 70s and before that, the programmer was trained for a specific machine. And that's one of the reasons why Unix was created, because for each machine there was a different way of working. So here is to add that layer, so you can think in abstract and you can use that with any underlying quantum resource that you have available. And the idea is to simplify also the execution. Okay, how to divide in between quantum and classical compute and all those things. It can be done. The idea is to find a way where it can be done very efficient. It's strange because when I talk about these things, it's exactly the same that I have to say when we're talking about how we are improving the resources for working with scientific code, for using parallelism and all those things. So what is the road that we have for the future? The road that we have for the future, it's a new architecture. We have to start thinking about how to integrate that hybrid proposal that we have known for many times. For example, Shor's algorithm is a hybrid algorithm where there are some things that are done classically and some things are done quantum. So integrate that into an architecture that can be seen as a whole resource for working. With the new version of Qiskit 2.2, if I recall correctly, is 2.2.1, it provides a software model that is defined by digital first abstraction. It means, remember, when we talk about digital, it's focus on the gates, not on gates on the circuits, not on the physical implementation. The smart compiler will be responsible for doing that steps that translate those abstractions into real code, into real instructions. What I mean by that is to real pulses, analog pulses that are used for evolve the quantum state. The HPC bridge, which is responsible for sharing information very, very, very fast. And obviously the runtime engine that will be handling how the quantum computing behaves. Okay. The idea is to work for a quantum serverless. The future of a quantum serverless means that you can think of the quantum resource. We have to think in a server, and all those things is part integrated into the architecture. That the user will submit abstract problems. This is a very interesting thing, that for problems that we already have a workflow that is very clear, that is automated, that meets the requirements of an algorithm, it should be written in code in order to improve the usability of these technologies. So it means that we have to add new layers that can solve specific problems, but that doesn't mean that there is no room for new research and for many algorithms. We are just starting. I always just say that if we compare the current status of quantum computing with classical computing, is like when we were in the 50s, when we start with the ENIAC, with UNIVAC, with all these, with the Mark I, Mark II, all these machines that were just opening the road, but there are many things to do right now. The idea is that if you have quantum center supercomputing, the idea is to compile, optimize, and run them across the whole resources. As in the same way that you today say, okay, I will run this in a GPU, I will use in ISIC circuit, I will use CPU for this, and I will use this number of cores, and I need this amount of memory. For the future, you will say also, I will need this, I need to run this in a quantum machine with at least this quantum volume and all the things. The release of Qiskit 2.2.1, it's a major milestone in this path. Okay, it took me 7 minutes more than I thought, but I will stop sharing the screen and I will open for any questions that you have.
Thank you very much, Juan, for the talk. Sure, we have a couple of questions now, and the first one is, what does digital level computing means?
Okay, that's a very big question, but I try to have an analogy with classical computing. When you are programming in a regular language like C++, Python, like Java, Rust, any language, you don't have to worry about the physical implementation, about the nature of the circuits, what kind of technology are the circuits using, all those things, because you have a model that is an abstraction of that. That model, in the case of the digital in the classical communication is that you have a digital circuit that is based on NAND gates. Okay, so when you are thinking about the problem, you think about the problem using logical operators and arithmetical operators. If you look at the history of computing, there is a picture that I really love. It's when the ENIAC was built. There are two of the researchers holding the ALU, the arithmetic logic unit. It was a very big device. We can do that because logic has a very interesting property that any logical operation can be written using only two operators, not an AND. And with that, you can build not only that, but you also can build all the arithmetic operations. You can represent the binary, the addition, the binary addition. You can build it with an AND, gate and a NOT gate. So when we move to a quantum computing world, what I mean is that we are using exactly the same approach. What is that? Is the following. First, we have the gates, the gates that we use, and we have a result that is very important, that there is a finite set of gates that can be used to represent any unitary matrix, that is the operation that we use in quantum computing. Okay, so it's kind of the same, but if you look at quantum mechanics, it's very interesting because quantum mechanics, it's a mathematical framework that is used for explaining many things in physics, especially in the quantum world. Why? Because the main equation that we have is the Schrödinger equation. Okay, and the Schrödinger equation specifies how the state of the system evolves in time, and it evolves according to a Hamiltonian, which is the observable of energy. When you are going to apply the quantum mechanical framework to a specific area, for example, in optics or something like that, what you have to identify is what is that Hamiltonian operator that is responsible for the evolution of the system in time. Okay, that means, and that's what we have with physical quantum computers. We have different technologies that are based on, that are behaving according to that mechanical, quantum mechanical framework, but are different technologies. But when you are designing the algorithm, you are thinking about the gates. So what is important to introduce this expression in this moment is because of the following, because when you are trying to write a real application, you have to tackle with the noise problem. Okay, and that's why, for example, the Qiskit Pulse library was used for how to control what is happening in the physical level. But with this approach, the idea is that you only have to focus on the gates. Which gates will you use? How you will build that circuit based on those gates? And the problem of how to map those gates to the physical computer and how to modify the analog interactions in that computer in order to minimize the noise will be done automatically. So, for example, when you are working with the current machines, you have a cluster and you have a node in that cluster, those nodes, the memory in those nodes have error correcting codes. So when the memory detects an error, it will fix the error, but will notify that there is a problem with the memory and we will have problems in the future. When you are building the program, you never have to take into account that there can be errors with the data in memory in that sense. So what we mean here when we use that digital, and that's what I made that statement before, that digital is not binary. Digital means discrete as opposed to continuous. Okay, so the idea is that you have to think in a finite set of gates that will be used for solving the problem. That they will be used by putting them in a circuit. You don't have to go to the physical details, at least from the developer point of view. From the center point of view, from the if you have a high performance computing center, it means that it will be responsible. That center will be responsible for how to translate those things in the more efficient way into the quantum code. For those who have experience in HPC, maybe you know about OpenMP. OpenMP is a layer that will help the programmer to build a parallel program that fully use the infrastructure of the machine. I want to be very clear in this. This is an ideal. This doesn't mean that in this moment we know how to do that. We know how to do some things. In fact, you can find libraries that you can add to your quantum computing, quantum algorithm to try to reduce the level of the noise that you have at the end. Okay, so you can use that. But we don't know yet if it will be, for example, if we can solve that for all the situations that will be, if that will be an automated problem for all the cases, or if I really don't think it will be that way. But I think that the developers will be focused on gates and circuits, and not on the physical machine that they are using. I don't know, that's answer the questions.
Yeah, thank you. Yeah, we have another one. In the Microsoft fiscal year 2025 fourth-quarter earnings conference call, Satya Nadella said, the next big accelerator in the cloud will be quantum, and I am excited about our progress. What do you think about this sentence? And could you give us our insights about, is QC replacing HPC? How is the integration in the cloud? And yeah.
Okay. Well, I think that we have to be very careful. In general, it's about the promises that we have from the different companies. Why? Because in this moment, if you're old like me and you have been for many years in the computing business, you will remember that at the beginning of the 70s, when the relational database model appears, it appeared not because Pierre Code was trying to create a unified model, all those things that will be used in all databases as a language, like SQL is an implementation of that, but he was trying to build a mathematical model to compare the capabilities, the query capabilities of the different products that were in the market. Now, with SQL, we have a standard. With relational algebra, we have a mathematical model that explains any relational database. It's not. It's very clear why models like MongoDB or all these graph-based databases or structured databases are built like XML databases. They have to state clearly that they do not follow the mathematical model of SQL. But all the relational databases have SQL as their base. So what I think is that in this moment we have many manufacturers with many approaches, not only from the physical side, but also on the tools that support that development and all the environment that is needed for running that are uh, in correct. It's right that they do that, but they are competing for getting attention in order to be the leaders in the area. So I think that many uh, of those claims that they have, we have this chip that can handle 1 million qubits or things like that. We have to be careful about that because what is important is not what they promise they can do. What is important is what we can do. Remember that in 1954, when the artificial intelligence term was coined in that meeting, I think it was in Dartmouth College with Minsky and all those people. They were thinking that in 1984 we will have autonomous driving cars, and that was 40 years ago, and still we have problems with autonomous driving cars. So one thing is that when we say we want to do this, and the other thing is that we are able to do that. So for all those claims that is the new development that will revolutionize the quantum computing and that we have the right solution and all those things, I think that we have to be careful and be kind of agnostic with that and try to check with reality, try to make a reality check in order to be able to prove if that works or not.
Awesome. Um, I will summarize three questions from Rafael. This are going to be extremely complicated, but really good questions. So, is the quantum computer connected to the classical cluster via TCP/IP interface? Um, do you have to set up an IP to the quantum computer, and they still use DHCP? And the last one that I think it's really nice one is, how do you power a quantum computer? Do they use regular 120 AC power supplies?
Okay. For the first one, to tell you the truth, I don't have an exact answer. I just will look at what has happened in the past. When all those protocols that we use, IP, TCP, were designed, they were designed with a different purpose. It was related, at that time, the world was in the middle of the Cold War, and IP, for example, was developed thinking um in how to keep the president always in communication with the militarist apparatus in order to decide things that can be as dangerous as using an atomic bomb. That's why today, when there is a crisis, when there is a catastrophe, when there is a big problem, usually the last communication that is lost is on internet, and the first one that is recovered is using internet because it's very easy to establish that. But if you look at that, you will notice that at the end of the 90s, there was a protocol that was designed that was called XTP, X Transfer Protocol, that was designed for applications, military applications specifically, where the idea was that you can remove different parts of the different layers of the stack that are not needed in specific circumstances. If you move to the centers, to the HPC centers, you will find that the first one were connected using obviously TCP, but then we moved to InfiniBand, which is a specific technology, a technology that was designed specifically for moving data fast in that context. It's not a technology to be used in the internet or things like that. It's just to connect nodes and nodes with storage in a HPC center. And I think we will have the same. We will have a specific protocols, a specific technology that will be designed with the goal of having a very fast movement from data from the HPC to the quantum computing and from the quantum computing to the HPC cluster. So that's for the first two questions. I forgot the third one. What was that?
About power, 120 volt AC supply.
Do you know that the energy consumption is one of the biggest concern that we have in this moment? I live in Colombia, and today in the news they announced that one big company, I don't know if it was Google, Amazon, something like that, was planning to build a data center in Bogota. Bogota is a very high city. It's at 2,600 meters of height. It's has cold weather and all those things, and they aborted that project because they couldn't get the guarantee that they have enough energy for doing that. I think that the quantum computing, but it's not my field, but I think that quantum computing will be more in energy efficient than the approaches that we have in classical computing. Okay, but it doesn't mean that we don't have to think about how to get enough energy to keep these things running. You know that in this moment, the energy consumption for artificial intelligence is very, very high. So, and if you add, for example, Bitcoin, the proof of work in Bitcoin, it's not. That takes a lot of energy consumption. So it's something that we have to deal with. And I think that the question is very important because if we are going to talk about quantum-centric supercomputing, we need to solve not only the communication, but all the information related to the management of the center. Okay, it means what resources do you need, how will be the connection between the machines, but how much power do you need, all those kind of things has to be solved.
Awesome, thank you. The next question we have, what is, in your opinion, the biggest problem until date that needs attention for researchers in quantum computing?
I think that the main issue with quantum computing is that you have to understand how does the quantum mechanics works. Okay, I know that this is a very difficult topic, and there are the traditional sentences like who says that understand quantum mechanics is because he doesn't understand quantum mechanics. But I come from the world of computer science, and the math behind the quantum mechanics is not that hard. What I mean is that it's a linear system. You have to work with complex numbers. You have unitary matrices, which is good because they always have an inverse and they have very, very nice properties. The observables that you have, they have to be Hermitian matrices. But the problem is that what is very clear from the mathematical point of view is not clear at all from the intuitive point of view. So we need to train people in order to think rigorously from the mathematical point of view in these things. And I think that the main obstacle here is that it's something that you cannot do at the end of the university studies or things like that, but it's something that you have to start developing from scratch, from basic courses, basic high school, middle school. You have to start training people because the problem that we have is how to understand this technology and how to develop this technology in two different ways. One, it's very important. Remember that quantum computing is no longer the dream of the physicists, is the nightmare of the engineers, how to build the machines that respond to the requirements of having a computing, especially how to reduce the uncertainty related with that technology. And the other part is that we have to develop algorithms. We have to develop new algorithms. Okay, keep in mind that when Shor developed the factorization algorithm, Shor's algorithm, it was, in my opinion, was a key point, a break point in the history of quantum computing, because they say, now we have an algorithm for solving a problem that has implications in national security and in electronic commerce. So we have to go in that way and explore more. There are many problems that are very hard, problems that are NP complete. Also, I don't know yet if I don't know, maybe if you know something about this, you can send me information, but I don't know of any NP complete problem that was solved using a quantum algorithm in polynomial time, because that will be the answer for the classical problem NP equals P. Okay, in this case with the quantum computing, but the general formulation of the problem is not that from a theoretical point of view, that will be a big step. But when we find new problems that can be solved using quantum computing, and that we haven't studied those problems just because the classical computing is not enough for that, I think that's where we have to focus research. First, try to solve those low-hanging fruits, problems that have big importance in the economy, like logistics, like drugs design, all those kind of things. But I think that there are a lot of space for doing research in how to solve things that we haven't tried because the restrictions that we have with the classical computing.
Awesome. We have a good one. Is it possible that quantum computers will eventually become as small and portable as traditional devices like CPUs, laptops, or mobile phones? What do you think about that one?
I want to make clear that I come from computer science, not from the physics world, so I don't know exactly if that will be possible or not. But what my answer will be in this sense. I think that we will have quantum computers as small and as portable as needed, provided that there are two conditions. First one, that is physically feasible to build it, so that you can build that machine with the things, because you can say one it's like what is happening with the Moore law. If you remember, the Moore law said that we will double the density, and we will double. In fact, it was the CPU's capability every 12, 18 months, something like that. But if you look at the history, you will find that the speed, the clock frequency was started maybe in 2011, 2012, and Intel made a very interesting marketing decision when they say, okay, for us, what we call CPU, now we will call it a core. And a CPU will be a collection of cores, and in that way we can provide that increasing capability just by adding new cores from time to time. And that's what we have in no. But in order to increase the frequency, we we reach physical limits that we cannot go further because it doesn't make sense. And it doesn't make sense because if you increase more the the frequency, you will the consumption will increase in a bigger way, so it's not feasible to do that. So the first condition is that you can physically build these machines. And the second one is that, excuse me, the second one is that building that machine and using that machine has to be more cost effective than using a classical computer. Because at the end, at least from my point of view, what is important is not if you are using a classical computing, a quantum computing, all the things. For me, at the end, the most important thing is that you are solving real problems in an efficient way. And an efficient way currently is not only in measure in time, but also in power consumption and money, how much does it cost, and all those kind of things. So I think that will be the two factors that will define what will be the smallest and portable quantum computer that you can build.
Alrighty. Another question, and this one will be combined with another one. If I have studied the fundamentals of quantum mechanics, can I prepare myself to make graduation project in quantum computing or quantum security in a period of 1 year? And I will extend this one with what skills do you need? What skills do you think a student and a person will need in order to work in HPC-enabled quantum computing, and how we need to prepare in order to be successful on this field?
Okay, then I will divide in two different areas. One is how to build quantum computers, and in order to build quantum computers, we need more people studying physics. That's clear. We need more people studying physics or engineering in like the application of physics, how to build systems using those physics laws. Because we are exploring something that is, we are now celebrating 100 years of quantum theory, but I think that we still have many things to do. It's just to look at all the discussions that are about the interpretation and all those things. But for doing that, we need people focused on that. And it's kind of what happened in classical computing. In classical computing, we have the following. We have computer engineers who are responsible for designing the machines, for the cooling system, for energy, for all those things. And that's one of the things, if you like to work on that issue, I think that there are many, many things to do there, because the machines we hope that they will evolve, and we will include new techniques and many other things. And on the other side, it's on the programming side. And if we go again to the classical analogy, we have computer engineer, but we have computer science. And on the classical side, on the programming side, on the developer side, what we need is people with a solid mathematical background for understanding what does a computer, how does a quantum computer works. You need linear algebra and you need complex numbers, mainly. That's what you need for doing that. But the big challenge is how to get a problem in real life and represented that problem as a sequence of multiplications of unitary matrix, or even better, how do you transform that problem into how to multiply a quantum, how to represent the information as a quantum state, a vector, unitary vector in a Hilbert space of on the complex of 2 to the n dimension, and find a unitary matrix that provides the answer that you find, that you want. Maybe since you transform the input, you need to transform back the input. You have to build an isomorphism in that, so you can return, but that needs a solid mathematical background. One of the main issues that I have found with the main problems that I have with my students, not only in in the university, but also when I train people from companies, is that they always try to find a physical analogy, how to understand what is happening in the quantum work, how to understand that from the physical point of view, intuitively. And it's not possible, at least for me. What I say that is, if you are interested in the physics, go to in building, go to the physics. If you are truly interested in development, you will need a train in math, not only linear and unitary matrices and complex number, but also need how to understand how you can map a problem to that. If you can transform that map into a quantum problem, then you can use that technology. But for that, you need to have a strong mathematical background.
Awesome. I have one on my own. That I want to know. I mean, based on your background, founding Apollo and handling a supercomputer, do you think that the integration of these quantum technologies to the supercomputing schema will change the economics of supercomputing and quantum? Today is extremely expensive. Supercomputing is not that expensive, but do you think that this is going to change in the near future?
I think it will change in the near future. If you look, for example, from the HPC computing, you will find something that is very interesting. There is a list that is called the L500, and that list has the following thing. They have a benchmark that is run in the machines that apply for that. Is run by the owners of the machines that apply for that, and they try to measure how fast is the machine based on the traditional measure that is the flops. And you have the R peak and the and the max peak, that are the values that the machine, at least in theory, will be able to perform. How many operations, how many flops you will get from that machine. But the interesting thing here is, if you look at that list and how it's behaved in time, you will notice the following: that every 5 years, the slowest machine of those 500 is as fast as the fastest machine 5 years before. And the fastest machine in that moment is as fast as the 500 machines combined five years earlier. Currently, we are talking, or currently we have, we say about that quantum classical computing is not that expensive. It's less expensive than quantum computing, but it's still expensive. The thing is that we now, when we evaluate the cost benefit relationship, it works fine. Okay, so I expect that quantum computing will not only evolve in capability, but that in the same way, and that's a hope that I have, we will develop new techniques, and the competition between the different companies will make quantum computing more affordable.
Awesome. One, we still have a couple of questions in the backlog, but Alberto is waiting for us to move on with the program. Thank you very much for participating in this version of the Qiskit Fall Fest. And if you want to stick around, we are going to have the talk on dynamic circuits.
I cannot say because I have a class 5 minutes ago.
Oh,
But
nice. But it's this is going to be recorded, so
yeah,
if anyone wants to access it, and thank you again, Juan, for um, for your presentation.
okay. Bye bye.
All right, bye. Thank you. All right. Our next talk for today is Alberto Maldonado. We have here Alberto Maldonado with us, and he is a computational scientist at IBM Quantum. He specializes in the application of quantum algorithms in the fields of machine learning and he has prior experience with other companies in areas that includes education, community building, software application, and he always focus on use cases like optimization, and he is involved in the implementation and development of quantum version of artificial intelligence and optimization models, and he's actually working on real world applications. So Alberto, thank you very much for agreeing to participate in this talk, and the floor is yours.
Okay, yeah, thank you so much for the introduction, Daniel. So, first of all, let me share my screen. Oh, okay, I just make the. Wait a moment. I think. Can you see my screen?
Yeah, we can see your screen.
Okay. Oh, I don't see. Okay. Okay, so you're looking at my presentation, right? Okay. Nice. So yeah, first of all, yeah, thank you so much for come here. I try to do this presentation about a different version of the characteristics we are working in quantum computing. We have different methods try to identify what is the limitation for different applications in different characteristics. Like Daniel mentioned before, I'm working in apply different use case in a real world with different problems focused on optimization and machine learning using a quantum computing. So the thing of this one is like in quantum computing exists different models. How can we need to focus? Not necessarily the algorithm is the goal. Probably the preprocessing, the post-processing, or the characterization. We can compile the quantum circuit or even try to optimize the transpilation part. Is kind of important thing. So in this case, we are working. What is the characteristic for quantum dynamic circuits, or what is the essentially part of working in this case? So yeah, basically the thing we are trying to do on this quantum model or proposal of the quantum circuits is just to put mid measurements. So what kind of characteristics we are trying to do in this case is like, okay, depends on the decision we got in the quantum circuit at a certain point of this one, we identify what is a certain characteristic. After that one, in a classical control operation, we need to identify a certain decision during modify in that moment the quantum circuit. You can look in this image in my right part of my slide. We had a certain characteristics. The first part is like we're starting to is the zero state. After that, one try to do a certain position of the quantum circuit just for that one create a bell state for the certain part of the qubits, and after that one try to do all entanglement. One of the things of this one is we try to create a mid measurement, but this mid measurement here, you can try to look 0, 1, and 2. We can try to reset the value. In this case, 4 could be 0 value because depends what it was. We don't know. It could be 0, it could be 1. So depends on the superposition in QR2, QR4, and QR6. It could be 0 once. We don't know. Depends of the probability we can do there. So in this case, we force the 0, but depends of the value we got it then we can apply certain conditions or certain we need to identify the expression value for this one, so we can create a boolean or arithmetic operation for the condition of this kind of measurements and identify it could be zero or a certain operation, a complex operation, or even a custom gate we try to recreate. For example, in QR3 we just identify what is the measure in the in the classic value 0. So in this means the M0, we just depends on the value we can apply a negation, or the direct summer or the XOR gate for the values 0 and 1 because we are working right now in a Boolean expression. In this case, because we are only obtained zeros or 1 here. So depends on the expression value, we can identify multiple decisions and do it are more complex characteristics at the moment to create or modify the quantum circuit. So why work with this method? So the characteristics of this one is like we need to identify other ways we can do error correction or try to do the quantum teleportation or even try to do a different way for variational quantum circuit in a hybrid way. Just to remark, in quantum error correction, we identify what is the characteristic for multiple qubits and try to transpose that information in another qubits, trying to get information and try to identify with and try to correct the value or identify where to ponderate, what is the most common value of the outcome, and try to consider what is the correct one, depends on this one. The other thing is why I try to do the quantum teleportation. The quantum teleportation, just a reminder, is just to create a superposition for a certain value and try to move in entanglement two qubit information that original information for the principal qubit we try to obtain the information. Well, that is sound complicated, but basically it's like in Q1 we put a certain random information we're trying to transfer in qubit Q2. So we try to do that value and try to recreate an entanglement between A1 and Q2. This is just an example just to describe more. And just after that one try to do a mid measurement between Q0 and try to coordinate the values for A1 and Q2. So that is the way we can do the transportation. And the other thing, probably, if you work with Daniel, when at the moment you try to recreate that quantum machine learning models, sometimes you need to do this proposal like quantum convolutional or quantum convolutional neural networks, or try to do this multiple layers sometimes, or try to reduce techniques is try to do this kind of correction using this measurement. In this case, it's like try to increase or try to avoid the number of the nodes for say something during the we can call in the quantum neural network and try to use to try to do the dropout way in this quantum way and try to do that. And yeah, for consequence or the goal for this kind of implementation is reduce the noise, reduce the information, and just to focus in the important thing we're doing is just set previous information during the circuit, not only in the outcomes for the final quantum circuit. Just depends in the mid measurement, we can just set information, and with this one make decisions during the quantum circuit. So the problem of this one, or what is the other things we need to do is like the hardware limitation we had in the connect the noise and try to identify the connectivity for each qubits. So the other thing we can try to do with this one is just reduce the depth at the moment to recreate the quantum circuit. Just to do the mid measurements, we can just to avoid swap gates or even the connection for non-logical or physical qubit and try to do the logical way. For example, when we're working in the right part, we're working with a specific hardware from IBM, and we try to connect, I don't know, this blue one for this one directly are not connected. So when we try to do the transpilation in this case, we can do just identify it's kind of necessary, but with the mean measure, when we are working with a problem or a qubit, when we're working just in this part, try to avoid this connection because it's not working at this moment. So in this case, we try to do like a lot of SWAT gates, and we're working with almost 100 qubit gates. What happened in that case is we try to reduce the number of the SWAT gates. So we try to do the SWAT strategies about that one. Other things is like depends on the characteristics of the nature. We can do if these two qubits are will be connected at a certain moment of the time. Well, just to do the connection with the bit measurement and do the control. So in that case, we can just reduce the number of the operation we try to apply in these two qubits, and for consequence in all of this one, because remember, when we try to do the SWAT case, is just three CNOT gates, and for consequence, depends on the nature of your backend, it could be more the cost when you try to do that one. So try to avoid that situation. The mid measurement will be helpful in the moment we try to understand more to reduce the number of the depth, the number of the circuits, and for consequence, even in the next era or in the noisy intermediate scale quantum era, we are used to reduce the noise for consequence and try to do this another approach. So basically, the thing we try to recreate here to understand how's working during the hardware is try to do the limitation and identify what working right now with the hardware. For example, in IBM, we had 127 qubits, but the characteristic or relevant part about this one is identify what is the characteristics, not just the number of the qubits. The other things is like the basis gates. The interesting thing about this one is at the moment when you're working with your quantum circuit, it's not just focus in, yeah, I try to recreate the Toffoli gate or multi-control gate and just it's just try to decompose in CNOT gates. No, in this case it's like ICR two qubit gate, the identity gate, the rotation C, the square root for X, and the X gate. So that means is it doesn't matter what kind of the characteristic of the reduction you try to do in your quantum circuit, you need to decompose in these characteristics. For consequence of this one is translate the depth. If you are had, I don't know, a basic examples like just a enough and a thing and a Hadamard, just not necessarily is a depth for two. It could be even 10. So for just a basic example like the build state, the consequence try to recreate with this hardware is just a depth for 10. So sometimes if you try to do like a quantum circuit and you had a characteristic for I don't know, 50, 100, that is not really true. Probably your real quantum circuit in this hardware could be like 1,000, 10,000. I don't know. It could be so big. So that's the reason sometimes the noise is so complicated to deal in. And the moment you try to work with a real or a big problem, and try to implement in a quantum circuit just is so complicated. So the things you need to identify is the characteristics, how many is the median for the react at error, the error for one single qubit gate, and the error for the two qubit gate. So that is the important thing at the moment. You just identify the depends of the noise. We can increase in depends of the number of the depth for two qubit gates and the depth for all the quantum circuit. So depends on the number of this one and the interconnection. So the most important thing we need to identify is how do the transpilation, what is the number of the qubit we have to do, is necessary just a specific subset of this one or increase all the quantum circuit. For consequence, we need to do this the swap gates. So in this case, we had noise and we try to increase this one is increase the error, the noise at the moment to obtain a specific solution for this one. And the problem when we increase the number of the qubits and try to identify what is a good approximation for a solution, for example, using QA problems, sometimes the most optimal solution it could be just 10 9, 11 shots for a specific state. So try to difference it could be the most optimal solution, not necessary. It could be just with one or two. So the things we need to increase the probability of this one or try to reduce the not optimal solution or try to reduce the noise. So with this kind of consequence, where is a variance fault solution or try to expect the most probability, that means no most the high probability solution is not the correct ones. It could be just a spectrum of the optimal top 10, top 20, or just the 25%. We don't know. Depends on your quantum circuit. Another thing is like the quantum circuit and depends on the characteristic we had or the nature of the problem at the moment working with the quantum circuit, that means it's not necessary correctly. So what is the thing? With different approach, do quantum error correction and dealing with that one and try to do error mitigation, try to decompose the quantum circuit, not dealing with the hardware, for example, the quantum error cancellation or probably probability error cancellation, sorry, or the zero noise extrapolation. So this kind of techniques is just try to do the approach of the noise and try to categorize in a certain way, try to reduce and using certain characteristics. Yeah, it could be like try to do a extrapolation way or try to do an inverse matrix for the original quantum circuit we try to do and just to reduce the noise. But for consequence of this one is try to do in a processing post the quantum circuit. So the quantum dynamic circuits, what is the different things? We can try to do or we can try to reduce at the moment to the sense the quantum circuit. So probably you can see this kind of a slide in the previous talk you working in the presentation for Ambient Qiskit 101 or not. But the interesting thing when I want to recreate of this slide is kind of very important because when at the moment we're working in quantum computing, we had a high level things when we are working with Qiskit add-on or Qiskit function where we don't know what is the thing. just to identify this is a good approach, a certain solution for application in simulation, and try to correct the error. It could be like you control things, keep a quantum for optimization, algorithms for simulation, and all of them. So at this point, it's just they try to confirm it's like a black box, but as companies say, yeah, working in a really good solution. So if you want to use these good results, just pay for us and try to solve the problems. So this is the moment when you try to identify more a solution or application things. But what is the moment where working or try to identify more in a low level? It's like it could be or working in the hardware, identify what is the characteristic, identify the calibration, try to do artificial intelligence decision with using machine learning to identify what could be the good approach or no. It could be worse. I don't know. I don't part of that one. Just I make a hypothetical idea about how working with the hardware. But I think we can do it, and it's more easy for us. Even try to do this kind of conversation is using just the software things. In this case, just doing with Qiskit. So in this case, we have certain implementation for different characteristics. Not just necessarily is the creation for the circuit. We try to do the transpilation part, try to the try to do the decompose for the hardware to do a good approach for the quantum circuit, try to understand this product specific background and implement different characteristics, different visualization, different information, and we had a certain analysis tools about how we can do the make decision for um, yeah, classical operations or conditional workflow. So in this case, with Kiski, we had a multiple nicely tools when we are working in not necessarily the quantum circuit. We try to recreate multiple applications and try to recreate the solution for biggest chance and just to do the connection with KPU using Qiskit transpilation and try to for a specific adjacent circuit where try to understand the specific basis gain and the specific characteristics for the interconnection KVX for the hardware and just to do the relation with Qiskit runtime. And the goal is like using a useful work for uses case we try to do, and that is the thing we are trying to do in Avian Quantum. Yeah, I know it's kind of a commercial thing, but the necessary we need to do is like just not necessary is just make a quantum circuit and try to do that one. And make a space could be just useful because when the moment you are working with hardware, even you are working with noise model, that means it's dealing with error, and the error is provoked with the noise. And we try to identify and reduce this noise using different techniques. But in this case, I will try to identify this kind of classical expression we're working in AVN. So exists different things: the expression, the construction, and the typing. In the expression we are working this basis characteristic when we are identify what is the decision after a classical operation depends on the type, sorry, and we can working with time, with a boolean or a variable in a general expression and try to identify in during the quantum circuit values or try to delay the characteristic for this one because the delay sometimes is necessary at the moment try to coordinate the values for a specific uh, interaction in this in a certain moment for the quantum circuit and create a really good state vector. What is the delay? Just don't do nothing. Just waste time for a certain operation. Is that the moment when we are trying to do a certain operation for a specific pair of qubits for all the quantum circuit, but the rest of the qubits is just not working. So in that case, just to do a delay. So that could be a function we try to recreate. So the things is the part for the expression is try to do a logical expression, try to recreate what is the in a certain way. The construction is this construction the tree is representation directly is the purpose and easy to make a mistake with the typing. So in this case, it's like depends on the characteristic of the model or the value you try to work during the expression. You need to identify it could be in the same way. So the best of this one, we had a certain type of values. It could be a boolean, it could be a time, it could be a unit. In this case, so in a low level, we are working in a classical way So in this case, we do consider immutable objects, and you you must not mutate them. So in this case, we don't change it. So we need to recreate and try to work with these kind of characteristics. For example, we are working in a classical way with a classical value or classical bit, and the moment we are trying to do a certain operation. So the operator we are trying to do is using this new part of the class in the Qiskit circuit. We are focusing this part of this class calling classical, and this will contain the expression. In the expression, we have multiple operations. In this case, it's just a basic one. We are calling logical. In this case, we are trying to do two inputs: the classical value and classical value. So in this case, at the moment we are trying to obtain the operation is a logical value when we are doing a certain interaction. So for example, focusing on application for a quantum circuit, I just try to recreate just to do a superposition of this one. So initially I just put, yeah, just a register. Randomly I just put three, try to do an interaction and modify certain values. In this case, I do a certain decision to do just to use two classical register. So in this case, I will start to doing this first two qubit a superposition with the Hadamard gates. After that one, I do a measurement in this specific two qubits, and depends of the value of this one, I use apply an AND decision. So in this case, it's like a classical in a classical computing. You remember what is the interaction for a bit or the application for logical into qubit for the AND operator is when both is equal to 1, the output is 1. In other case, is equal to 0. So in this case, just apply another modification. In this case, you just validate when it's equal to 1, just apply a negative value. It's like, okay, in that moment it's not working, just put the negative, these two values, and after that one try to evaluate the last two qubits, no, the last three qubits again, for this one. So in this case, the tricky part at the moment, try to do the quantum dynamics circuits is just to put with measurements. The best of this one, we evaluate what is the characteristic, what's the relevant part we try to recreate during this quantum circuit. And after this question is try to do, or is like we need to apply something, we can reduce the characteristic of this one or try to, yeah, hide the probability in a certain decision for the operation of the value of this one. And the best of this, we can put any gates to remark the operation or the goal we try to do, and use the same quantum circuit and the same quantum register and the same classical register. The case is with the classical, because in this case we just don't lose the information, just to rewrite the information and obtain the same outcomes. Because this could be done axillary, we can create with more classical register, but this it doesn't matter because it's like a temporal value. So the mid measurement just a temporal value depends on the decision of this one. We try to obtain a certain operation. After that one, we try to identify a certain decision. So the final decision or the final measurement is the relevant part, because of this one we can know if it's working on dynamic quantum circuit or no. So just for here, you have certain question, certain doubts.
Yeah, we actually have two questions so far.
Okay.
Um, what are the real world applications where these quantum tools have been successfully used?
Again, can you give me the question?
What are some real world applications where these quantum tools have been successfully used?
Okay, are you talking about the Qiskit functions or the things we're doing in Avian?
You can answer both.
Okay, well, the skill function we have, well, we identify with this partnership what kind of application with the state of the art and different papers if they are working at really good results, and identify what is working these tools is more like it's a black box for us. Just this partnership gives us the information are necessary for this one, and just to supervise is necessary for our real cases for our future clients to do the connection with the clients. And the other things is like, well, so in fieldworks is like they need to prove they're really good for us and for the clients they expect to use these tools. And the other things for Qiskit and this way, yeah, it's like we are doing different papers when we identify the limitation for the quantum computing compared with the classical. So you also remark for this way, there's like in quantum computing, we don't know just to use for usage. This is no, oh yeah, exists quantum computing and we're working with hardware, we just execute because we can. It's more what identify the limitation for a classical way, identify what's the limitation using a quantum computer, and to do the comparison or do the big question. Is necessary quantum computing? And the answer is yes. In what kind of situation? Or if this problem is possible to use in a quantum computer? And the answer is yes. Well, what is the state of the art? We can use it and try to do that one. So the answer is that one is just to not to use hardware to use it. Is identify the limitation and try to identify the limitation in classical, the limitation in quantum, and for us is do research and improve both sides and say the decision. Yeah, quantum computer is here, but we can identify a better solution for that one using a reference the state of the art. So basically, is doing our research at the moment, but focusing on specific use cases. So basically, that is the thing. Just not thinking, oh yeah, I'm going to use hardware and try to see what happened there. It's more be as per of the specific topic, identify what is the characteristic of the different option we got it, and yeah, if this is possible, it's possible, and working on that. So try to do the Kiskin function for other companies is because they prove that could be a good option, but that not means it's the real one option. Another thing is like no, because we're trying to do that one is just to identify yeah, X is just that solution. Even you had another proposal during your undergrad, master, or PhD, and say, oh yeah, I had this idea, it could be very helpful, and you create a paper, yeah, that will be helpful. So that not means just try to do an answer and say, yeah, we got the goal. We are in this community at this point, identify all the possibilities, and yeah, if it's over for other university, other company, it's good for us because that is the part to do research. It's not just useful for the company. That is the thing we are make and write papers is like we identify what is the most useful for the society and the academia or the industry and trying to increase the other solution for us with the capacity we're working right now and try to explore the limitation we got at this moment with the quantum hardware and the KPUs and yeah, you obviously using our SDK case kit. So yeah, I just to remark this one with this slide because it's the thing we are doing. So that is my answer, Daniel.
Awesome, awesome. Thank you very much. We have two more questions.
Yeah, go
The
ahead.
next one is what is the difference between the Qiskit add-on and Qiskit function? And as a developer, what do you need to develop in these components?
Okay, the custom function is most like a black box. Is like when you're working or you install certain predefined in other areas. Is like I don't know. For example, when you update a specific library, you don't know what is behind, or you don't care in that point. So there's moment when you start working with Qiskit, you don't read all the manual or what is the meaning for the function. You just look an example and you execute. So basically, the Kiskin function works in that case is like the company's mention is like, okay, this project is working for optimization, this work for mitigation the noise, or this is the calibration part, or this is used for chemistry or simulation things or whatever or quantum machine learning things. So the things they say, this is the input, this is the output. So we don't know what is behind that part. It could be a good optimization, a bad optimization. We don't know. It's just this company is working on that, and just Qiskit do a good, yeah, connection with the Qiskit support with the hardware with Qiskit runtime and validate it for this company or the results they got it. It could works in certain ways. The Qiskit add-ons is another way where we're working in AVL at the SQD. After that, when depends on the characteristics you are doing, could be the pre-processing or during or after or post-processing. when you are working a function specific to help you to obtain a specific results in the problem or the project that you're working or looking about that one. Like the Qiskit SQD, this is a procession for diagonalization, is more focused in Qiskit simulation part. Even you'll be part of the Qiskit Summer School 2025. I think the lab four of yeah, I think it's lab four or lab three. I don't remember exactly. I think it's lab four. You are working on that, and the idea is like yeah, try to optimize yeah, post processing about that one. And developer skills about this one is really necessary because at the moment you know how it's working and everything is changing. And not it's because in Qiskit we are changing the things because we want. It's because everything is changing. Not necessarily the Qiskit. It's like all the state of the art we need to increase and do different improvement. And the thing from Qiskit is just not the Qiskit circuit library. We had a lot of different things we try to do. Even in the transpilation part I worked on before is more characteristic for attack. And that is like a graph. So you are doing a theory graph implementation in the quantum circuit. So you're interested to do a software developer or quantum software developer. Depends on the topic of your area. You are doing a certain developed skills using implementation, the Qiskit add-ons, or even the visualization, the deploying for the Qiskit runtime, or even focus with Qiskit too. And the other thing, when at the moment you're doing a research, like is my case, you are doing a data scientist tool. So in my case, is I need to do good developer skills to identify a certain problem, and after that, I want to analyze the information about that one and try to do a general interpretation for multiple audience. It could be other audience like a research for my level, or even it could be a general audience who has no knowledge about that one, but are interested for results for the user case solution, or even for a general public who is not interested in this one, but is interested in a certain topics. So basically, the thing at the moment working with developer is necessary. Yes, definitely so necessary try to program and understand this one. If you are trying to use or solve a use case, but they are more, it could be work in a theoretical way. That is okay. You're working just theoretical. It's not necessary to understand all the function of the Qiskit or the quantum circuit. Just more focus in the theoretical way and to do use Qiskit just to validate yeah the your theoretical information, your proposal you are doing. So yeah, Qiskit is a really nice SDK because you can explore for different aspects and the thing you are trying to do. Even like the tools I'm doing, the classical is more a certain level you are recognizing a classical computer, but doing the interaction with the quantum computer. So the interesting thing is, imagine you are doing a hybrid operation using a quantum personal unit, so quantum processor. So it's very cool. Try to do that one. Yeah, it was another question, right?
We have two more, and we are
Oh,
going to abuse of your time a little bit here with this too. Um, so, do you want to choose one? One about the presentation, and one about your perspective. Which one do you want first?
my presentation.
Presentation. Okay. I got confused on the first part of the talk when you're explaining the basic idea of the DQCs. Are you saying that mid-circuit measurements can substitute swap gates when transpiling
Mm,
accuracy to a
No,
certain hardware?
not really. It could be a possibility, but not is the goal. It's more depends on the situation you want to do because the interesting thing about this one is like here in this example is you know what is happening after that one. Yeah, it's a measurement here and it's a connection for a gate. But here is like sorry. And but here is like we know it's zero because after that when we reset the information value, so we can do a certain activation for this one and identify it. Instead of apply here a CNOT gate, just put this mid measurement, so avoid a 2 qubit gate here. It could be one thing.
You-
The other
You're you're not sharing your screen.
sorry.
Yeah,
Uh, let me again. Here.
there
Can
you
you
go.
see now?
Hmm.
Okay, the thing is, the first thing is like exists multiple options. You try to do the dynamic circuit. The first thing is like if you know what is the position here, you know you don't need to change too much. You can apply the mid measurement, and for consequence, here this is a more complicated situation because here is like well, this is a CNOT gate because just to depends on the value for here, you apply a gate, a X gate, so it's CNOT. So apply here is like okay, I apply here, but I lost information to apply another CNOT gate. But what happened here? I meet two CNOT gates here because make the decision for N1 and M2. And here is another three CNOT gates. So it's N2, N1, and N3 just for apply this Q2 qubits. So here is one CNOT gates, two CNOT gates, and three CNOT gates. So in total is six CNOT gates. But instead of using three CNOT gates, I used to work with three CNOT gates and these measurements. So I reduced this problem with three CNOT gates compared with the original quantum circuit I'll try to do. So this is another option we try to reduce because reduce three CNOT gates is a really good one. It's like I reduce a SWAT case because do you remember three CNOT gates is equals depends of the combination is a SWAT case. Or for other words, the decomposition for a SWAT case is three CNOT gates. So that could be one option at the moment we try to reduce the noise in the quantum circuit because we reduce the two CNOT qubit gates and for consequence we don't need to apply or increase the noise in a quantum circuit. That could be one. The other thing is like, yeah, here, what happened here in the same example in the qubit QR7? What happened? This connection QR2, QR4, and QR6 are connected directly, depends on the hardware, but in your reminder is just we had in the best case three, four qubit connected. It could be four, six, and two. But what happened with other case? Or what happened the connection with this one? It could be works, yes, definitely. What happened? We're working with this case. It could be the another one. So instead of doing a good connection here, we can try to do this connection, this gate, the QR7, it could be not part or related or connected directly or physically. So instead of to do that one, just to apply ambient measurement and do the connection directly. So we can avoid to splice SWAT gates and do that one. So it's not necessary just to avoid the SWAT gates. It depends on the nature of the characteristic we are working. In this case is the physical qubits and logical qubits. The logical qubit is just this one because it's just pure simulation. All are connected, all is nice. But what happens when it's created with a physical qubit? At the moment you don't know. It could be the SWOT gates applied here, but at the moment when I create this one, it's just not necessary because it's not connected directly. So when do the measurement is directly because the connection or the how can I say the connection is with the mid measurement. So the classical bit is connected with this one. So for consequent here we reduce the quantum circuit and when do the transpilation we reduce the possible SWOT case we had at this moment. So that's the two nicely things we can do it at the moment to implement the mid measurement of the quantum dynamics circuit. I don't know if it that solves the doubt or is more clear my explanation.
Yeah, I think it's good. But actually, I have a follow up on my own on this one. So
Yeah,
you first collapse the state and then you reinitialize that qubit.
yeah. It could
Okay.
be that could be depends on the value you are interested. Even that value you can still works. That it could be up to you. And the other thing is like it's necessary. What happened here? What happened I tried to do a measurement in QR and instead of using this CNOT gauge, apply a mid measurement. It's like it's necessary to put a reset here? Not really, because QR0 is not working for us. It's not interested for us
Mm.
anymore. Just is a pre qubit just to do or recreate the Bell state and start to do a superposition value. So we can do that one just to apply here a mid measurement and
Yeah.
this just to avoid because it's not necessary.
So right now we can create a more accurate simulation of the teleportation algorithm, mid-circuit measurement, get the bit string, and then continue, right?
Yes, exactly.
Yeah. And the last question we have for us, it's the next one. The main problem with validation of output, the quantum error or noise. If we use multiple processing units, run parallel and average out, or like filtering based on the similarity of the output in the waves. According to me, it may help in making the output clear. So the question is based on this rationale. What is your view in its practical or is just a hypothetical concept of basically having the average of the different measurements?
Well, I'm working in this one and it's not open right now, but I think when you apply the mismeasurement and try to recreate everything, depends on the value is like this way. It's like what information is necessary and what is not necessary. The other thing, in my case, I'm working on certain experiments. I cannot show it, sorry for that one. The thing
Okay.
is like I keep certain interest qubits where I try to optimize the probability to obtain a specific good answer. In the other case, it's just the conditional values. So in the conditional values, I can do the mid measurements just to identify what is the correct one and modify or alter the values of the probability for the interest qubits. So that for consequence, I do it. That one is reduce the number of the gates and reduce the noise. Even when I try to do the original version with my modified version, with a depth for 1000 gates, it's still working. The dynamic circuit give me the optimal solution in a correct way. So in this case, yeah, definitely it's important to see what is working in this characteristic in the hardware in your quantum circuit. But that is the thing, is like not all the circuits when try to move or try to do this interaction with the quantum dynamic circuits is identify the value. It's more like yeah, here this example is depends on the mid measurement. We need to modify certain part or certain subset of the circuit because that part you need to modify is more interesting part. The other thing is like optional to identify. So at that moment, you are not really interested in that part of the system. So in that case, you are just to modify the reduction space. For example, you had a spectrum for, I don't know, 10 qubits. You had 1024 possible options. So if you do it a mid measurement or this case, you are interested for the 10 qubit? Probably no. Depends on the problem. We can think you're just interested for the half, so 5 qubits. So in this case, you are using 512 states. So that is a good challenge. But what happened instead of using the 5 qubits, you're interested just to the half two. So it could be 3 or 2 qubits. So you only need no, sorry. 5 qubits is like 64 states. Yes? Oh, no, 32. So in this case, you are working with only 16 or 8 qubits. So the best of it when you are reduce the sample for possible states. That is nice. But what happened there? What happened? We are trying to so we're increase or reduce the states. We're increase the probability for the interested things we are doing. So that's the same things we can do it with the mid measurement because instead working with the temp, what is the interesting thing? Five. Okay, so instead working with 1024 state, we can reduce with 64. So the other possible state are not necessary for us. But at the moment when we try to do the mid measurement, it's like okay, we avoid that unnecessary state because when we measurement the previous states or the other qubits, we alter the state where necessary. The 32 state is possible for or are necessary for us. So in this case, in start with a big stack vector, we are reduce the value of the sample for that one. I don't
Thank you
know
very much.
that it helps the explanation. And I don't know if it's more questions.
Nope, that will be all of our questions. Thank you very much, Alberto, for your presentation, and we'll go
Just
on.
I want to do, yeah, that is the thing I want to make next
Okay.
steps because yeah, I don't know if you have this slide yesterday, but uh, probably you know the last week it was open the internship program for Navien. So you're interested in working in Navien Quantum in the next summer. Exists different roles focus in hardware, software. Yeah, you can take a look about that way. So you just go to IBM jobs and put the caseworks quantum and internship, and you can see all these internships you can get it. And yeah, it's a really nice experience. You can see in the middle is a familiar face. After this internship, even you can work in a full time. So it's possible, and it's a really good experience. So you're interested to do your undergrad, master, or PhD. It doesn't matter your country. You can apply and see what happened in this case. And yeah, you are not interested to do an internship because you are a beginner people and say, yeah, I need more skills in quantum computing. Well, exists the Qiskit K program when we have this opportunity to do the mentorship, the networking, events, and recognition in the community from ABN and around the world. And in this case, we had a certain opportunities, depends of the points you got it when at the moment you convert in a Qiskit a member, you had the opportunity to work with ABMers to yeah, to do certain solution in the uh, pull requests we had, or yeah, certain issues, you can try to solve it and try to do educational things, research, or even software things. Obviously, you had the opportunity to do networking with this big community and try to support different events like the hackathons, the Qiskit challenge, or even try to yeah be more detailed, like to do your own Qiskit Fall Fest, like Daniel do that one. And we had in a near future, hopefully, to do the Qiskit developer certification for Qiskit advocates to do a voucher. Is this possible or no? I don't know at this point, but hopefully it could be do it. So basically, the Qiskit advocate or the opportunity I'm trying to do is because, yeah, the Qiskit, well, I prefer this group. So the idea is try to recognize the people, try to make more opportunity and a friendly way for people who are interested in quantum computing with this Qiskit community and make relation operation and way to do this kind of seminar when we try to share knowledge, share experience, share opportunities with other students, even educator research related with quantum computer or people are starting in quantum computing and make a career with this area. Yeah, you can do it. And yeah, I invite you to do a Qiskit Advocate and participate on this one. So you're interested, let me know. And yeah, if this is more information and this is the link, you are ready to be a Qiskit community. Yeah, advocate program. Yeah. If you have more information, you can see this link. And yeah, that is my commercial. Sorry, Daniel.
No, you're good. You're good. This is always really really good information, and actually it's a really good starting point if you're thinking in a career in quantum. That's actually how most of us meet. Actually, I know Alberto for like 5 years, 6 years now, and we haven't even meet online in person once. Thank you very much, Alberto. We really, really appreciate your talk, and we are going to continue our activities after a break. We're going to have a lunch break, and we will be back at 2 p.m. with our next presentation that will be on transforming technology and policy design, where we are going to have Avanti Josh, a Congressional Innovation Fellow at Tech Congress 4, speaking to us. So see you then at 2 p.m. Eastern Time. and we are going to be in touch then. Alberto, thank you again, and we will keep in touch.
Thank you. Hi
All right.
everyone for listening me and taking some more yeah to listen my comedy show for 1 hour. So yeah, see ya.
Yeah.
Bye.
See ya. Thank you.